because of a loss in a dependent frame, in a reference frame, is more or less the same as the number of affected pixels in this first frame. So we will take these two effects into account to describe our distortion model. The expected distortion introduced by a frame results from adding up the expected distortion introduced by each of the packets that transport information that belong to it. And now first we will, so this is the place in which we will go down to the two packets. First we will consider that there are no references of this frame, so we will only consider the impact that it will have on dependent frames. And we will model in the following way. So we will model the number of pixels that will get affected by the loss in this very frame where the loss has taken place, and the remaining dependent frames in the sequence. And this is this number here. And we also consider the likelihood of this packet being the first lost one in the frame, because if it weren't the first one lost, the other one will cause this loss of synchronization, and ours will have no impact on the following frames. Now we will consider the effect of references in the impact of a frame. To do that, we first consider the impact of simultaneous errors in one frame. So if the value of a pixel is modified by one loss, another different loss will not affect it any further. So that this is different to what happens when using the PSNR or other metrics of the kind, as they consider the difference of value. And also, if we consider any other models in which we don't take into account the references. So if a pixel is modified and could be modified by more than one packet loss, we have to assign this responsibility to one of the packets. And we do so according to the encoding order, and so to the, of course, to the dependence relations within the string. And that leads to assigning this responsibility to the first packet that is located in the string. This also is consistent with the effect of loss of synchronization that we have seen previously. So we can see that on these figures in which this area here that could be affected by these two different losses is finally assigned to this packet here. And so this loss affects the impact of this other packet. And this is considered in our model. These similar scenarios are considered in these other figures. And so this is all formalized in this following way. The distortion is introduced by a frame, depends on the different packets that belong to this frame, and also to the effect of reference of packets belonging to reference frames. They will also impact ours in the sense that the distortion that is introduced by a packet is affected by this other packet that belongs to a reference frame by considering the area that can be assigned to the packet under study. We first consider its impact as an independent packet, and then we will consider the effect of the other packets in the reference frames. And so finally, this is all evaluated through the simulation of the transmission through a channel which we have used as well a general model. And we have compared our distortion model to a distortion model, a model in which the references are not considered at all. And so to perform this comparison, we have used the unequal error protection extension that we have developed, and we have also used the optimization technique that we have designed. And what we can see here is that for different packet loss rates, this is the average number of affected pixels in a sequence, and that with our by using our distortion model to define the relevance of the different packets in the stream, the unequal error protection extension that we have used, this unequal error protection extension, can perform better, which means that it can more accurately model the different packets, and so we can better adapt to these characteristics. So we'll conclude this talk with conclusions to the different points of the thesis. First, a general remark: we have developed a framework to extend the range of operating points and improve the performance of the ProMPEG COP3 codes. Regarding equal error protection extension, we have introduced this third new dimension to increase the number and the quality of the configurations that can be used. Regarding the unequal error protection extension, we have introduced the possibility to use more than one packet to arrange the differently relevant packets in the stream. So these extensions provide the COP3 with better performance in terms of final packet loss rate or with better final overall distortion. Regarding the optimization of the unequal error protection framework, we have introduced a new metalistic that is based on the core procedures of simulated annealing and double search that is used to quickly look for near optimal configurations that can be used in our scheme to protect data packets. And finally, we have developed a packet level distortion model that more accurately can model the distortion of the different packets in the stream, so help unequal error protection schemes perform better. This is a list of the publications that resulted from the work of this thesis. Finally, I will address some points of possible future work approaches. Which, as a general observation, first we would like to bring this unequal error protection extension idea to other equal error protection codes, for example, with Solomon or LDPC or Raptor. Regarding the equal error protection extension, it seems logical to make